Good morning. This is Lecture 8 of Mate Technique 2013-2014, Monday, 16 December 2018. This is Edwin Carlin giving a lecture for the University of Twente in the Netherlands. From the University of Tsubei in Japan. Today, our lecture is about translational motion, displacement, velocity, and acceleration sensors. So today we'll talk a little bit about the phenomena of measuring displacement, velocity, and acceleration, and then some types of sensors that are available to make these types of measurements. In the second half of the lecture today, I will talk about mass, force, and torque sensors. Please note that homework number 7 is due today. This is the homework Dr. Wouter Oldhaus on chemical sensors. There are 2 problems. Also, homework number 8, homework assignment number 8 is available on Blackboard this morning, 16 December as well. So translational motion, displacement, velocity, and acceleration. As we all know, movement is an integral part of many systems and sensors, and measuring these motions are important tools for engineers and scientists. Today I will talk about translational motion, specifically displacement, velocity, and acceleration. Then I will talk a little bit about vibration that uses the oscillation or periodic motion of a particular body to be able to detect acceleration, motion, and also shocks. For example, an accelerometer uses this type of vibration sensor where a proof mass is vibrating at a particular frequency. When the sensor, which is typically attached to a particular body, accelerates or decelerates, that mass will move and it changes the resonant frequency of the sensor. And this is what we detect typically with an accelerometer. And you've had some experience with this in the practicum sessions. The quantities in units that we'll talk about for distance, velocity, and acceleration sensing are length, which is meter, strain. So remember that strain does not have units, and we're talking about linear strain. Velocity, meters per second. Acceleration, meters per second square. Angular displacements, radians. Angular velocity, radian per second. Force, which is equal to mass times acceleration, is in the Newton. And torque, which is a force moment, is Newton meters. And that symbol is tau for torque. So for translational displacement, we're going to discuss 6 different types: a resistive potentiometer, a linear variable differential transformer, LVDT, which you've also had some experience with in the practicum, a variable capacitor transducer, and you've had already 2 examples in the homework, so you are now experts in calculating the response of capacitive-based transducers. Variable inductance transducers, you've also had some exposure to these earlier in the course. where we have magnetic field lines that are influenced by a moving core that influences the magnetic field and also then the current that's driving the magnetic field in a loop. Strain gauges can be used to measure displacement, and we'll see examples of those. And then optical, which is new. We haven't talked about optical sensors at this point in the course. This is an example of a resistive potentiometer. Very, very simple. Essentially, the wiper arm of the potentiometer is connected to a moving entity. In this case, a water level is pushing up on a rod and forcing a torque and moving the wiper of the potentiometer in a particular direction in the upper right-hand picture. And then in the upper left-hand picture, you can see that the measurement voltage that we measure is then a function of AC over AB multiplied by the potential that you apply to the sensor. So the output is then going to just be a function of how the wiper arm moves, as we know with potentiometers already from our high school days doing simple electronics. However, you can see that typically with a potentiometer, don't have a smooth transition in the output voltage as we move in displacement. We have little stair steps, as we see in the lower right-hand figure. And this is primarily due to the wiper fingers have a finite size. And as they move across the lower core of the potentiometer, it's difficult to make a linear and perfect transition between the core windings. And remember that the core windings also have a finite space. So these stair steps that you see have to do with the finite width of both the fingers and then the core, which is located on the bottom. But for coarse measurements, this is a very simple and easy way to do an electronic measurement of motion. Linear variable differential transducers. In the upper picture in the center, we have a primary coil that has our drive voltage connected to it. And then on the right, we have our secondary coils, A and B, that we detect. They both give a voltage VA and VB. The output voltage then is a combination of VA and VB. The core in the center is connected to the entity that we want to measure the displacement. As that core moves, the coupling between the primary coil and the secondary coil changes. For example, you see the output voltage V out or VA is equal to this coupling constant times the driving function, which is in this case a sine signal. Now in the central position, VA is equal to VB, so then V out is equal to 0. If the core displaces upwards this direction, then V out will equal to K1 minus K2. And you have some experience with this already. A very simple way to measure displacements, but also it can be quite accurate. Depending on how you do the readout. And this is an example of using synchronous modulation, the LVDT sensor. So if we apply a sine signal to the primary coil, and then our center core is moving, then the output is actually going to be modulated by our original sine signal. So we want to be able to then pull out our displacement. So that means we have to use a synchronous demodulation circuit on the right-hand side, and also with this multiplexer on the bottom, of the circuit, this forms a synchronous demodulation. And you can read through, it's a very simple procedure. On the bottom, we essentially create an auto crossing detector and create a square wave with the switches, this analog multiplexer, and this square wave then goes into this RC capacitor circuit, and then the operational amplifier on the output. And this circuit then demodulates the motion of the central core. So then you will get a voltage that's just a function of the displacement without this modulating sine signal from this operation. This is a really interesting and simple way to do, and it can be quite accurate way as well to be able to modulate the movement with an AC signal and then demodulate it. And we've seen some of this synchronous demodulation in one of our earlier lectures and also in our homework. Variable capacitor transducer. So this looks very, very familiar to one of our homework problems where we have a cylindrical capacitor. So we have an inner electrode that's connected to the entity that we want to detect. The capacitance, as we saw in our homework, is going to change as a function of this displacement. Another variable capacitor transducer, in this case, we have parallel plates, and we have two circuits located in B, which represent the same circuit, but the central plate is the part that's going to move. Now we have parallel plates, and in the zero motion position, our output voltage then is going to be 0, and the capacitors C1 and C2 are equal. Now, if that plate moves down due to a displacement that's connected to the entity that we want to detect, then the second capacitor will get bigger because D, it's inversely proportional to the separation of the plates. And then the capacitor C1 is going to get smaller because the separation, the gap separation between the plates gets larger. And then we're able to then decode that change in capacitance to an amount of displacement that the plate moved. And in this case, the upper plates are in a fixed position, and the central plate is moving in the Z direction. This is another example of a variable capacitor sensor, but in this case, this is called a proximity sensor. So essentially you'll see that we have a primary electrode, and then we have a shield, which is labeled driven shield, which is this hashed mark, large hashed mark, which is in the center electrode. And then we have a case, which is connected to ground. Now the purpose of the driven electrode is to apply the same potential to the driven electrode that you do to the primary electrode in the center. And in this case, we don't have any electric field lines that extend between the shield and the electrode. However, we do get fringing fields from the primary electrode to the case. And as this proximity sensor, as you change the dielectric in front of the sensor, let's say we have an object. Normally this is in air, so our dielectric function is then equal to 1. Most objects have dielectric constant greater than 1. As an object comes in close proximity, then the electric field is going to essentially change because of this changed dielectric material that's changing the electric field pattern from the electrode to the case, and we can detect that in a voltage change with this follower circuit, and then our output is going to give us relationship between the output and the distance of this particular object with respect to the electrode plate. Quite a simple concept, but it can be quite effective. And you can basically, by placing this driven shield, this provides a much higher sensitivity to compare it to not having a driven shield located in the circuit. Another variable capacitor transducer, very similar to our homework problem as well. And in this case, we have stationary plates, M, K, N, and S, and moving plates, P and Q. And the moving plates in this case move in the lateral direction. And then we can also put this into a bridge configuration, as you see in the circuit on the bottom. And then we can calculate our output, which will be a function of the movement, the lateral movement in X. Very similar concepts to the homework problems that we've already done, and then this output amplifier that you see on the output. Now remember that this is the circuit that's drawn here, doesn't have the operational amplifier that's reading out this voltage, doesn't have the RC network, the integrating circuit, and all of the feedback network into the amplifier. It's just not drawn there, but in reality, all of those components that improve the sensitivity of the measurement are included in that operational amplifier, in the feedback network, etc., as you've been doing in the homework. Now we can also do a variable inductance transducer and put that into a bridge configuration. Okay, in this case, displacements of the core on either side of the null position, and the null position is when your output voltage is 0. So when this core is moving, then you're going to get a finite output voltage. And you can see with this bridge configuration, you have an AC driving signal, and then you have in two legs resistors, and then you have inductors, winding A and winding B. And essentially how this operates is when you have your core in a particular position, you tune the output voltage to be 0, and then when you get a finite movement of that core, then you get an offset, and you're going to generate an output voltage that's proportional to the displacement. So all of these sensors are very, very similar in the way that you detect this movement, and these displacement sensors using when you're doing it electronically with a capacitor or an inductor, it's very useful to put this into a bridge configuration, because in the null position where you don't have any displacement, you can always tune the output voltage to be 0. And then if you're moving in, you can always set the movement to work in the linear range of the amplifier. So the bridge configurations for doing these displacement sensing is very, very useful. And you will see a bridge problem on the homework and the exam. Now, we can also use strain gauges, and a strain gauge, in this case I will describe essentially a conductive material that has a finite resistance, and as the material, which is elastic, as you bend it, for example, the resistance is going to change. And this is called a piezo-resistive effect. So when you strain the material, the resistance is going to change, and then we can detect the displacement based on the amount of strain. So we have to characterize this when we apply a certain amount of strain, and remember, strain can be Let's say if you're pulling something, it's delta L over L. But the strain can also be characterized with respect to the change in the resistance over the unstretched resistance and the gauge factor. So remember that the gauge factor is the delta L over L divided by delta R over R, right? And that's our strain. So remember that you're going to have to use this in the exam to be able to calculate a system based on the gauge factor, similar that we did in the homework. Now these are examples. Most strain gauges have a gauge factor that's around 2. There have been some platinum alloys that have been the gauge factor is increased, but many now strain gauges are made out of silicon, because you can see that we get an almost 2 orders of magnitude increase in the gauge factor when we use silicon or polycrystalline silicon. And in this case, you can see that the resistance then is equal to R sub 0. And R sub 0 is then the electrical resistance with no strain applied, multiplied by 1 plus Ks. And S here is strain. Remember, that's our quantity. And then the gauge factor K. And these are 2 examples of strain gauges. On the right, we will see this old-fashioned wedge type of displacement sensor, where we have this material that's kind of branching out and then a wedge that goes in between these, and a strain gauge is put onto these materials that, as the beams are moved due to the wedge moving deeper, it basically spreads these beams in the right and left directions respectively, which induces a strain. So essentially this area is going to stretch, and then the strain gauge is going to be elongated, and then we get a change in the resistance. Typically this type of sensor is made of one of these alloys or metal conductive materials. But a more modern way to make strain gauges is the picture that you see on the left. This is made out of silicon, and these are microsensors. So these types of sensors have been made in the nanolab at Mesa Plus for many, many years. And essentially, on the lower picture, you can see that we have 2 parts of this. One is a diaphragm. So both of these are made out of silicon. The diaphragm has these supports. Everything's made out of silicon. And then these resistors, R1 and R2, are silicon, except that we put an impurity like phosphorus or arsenic or boron into the material, and we make a resistor. Now, as this diaphragm deflects, then that surface is going to stretch, and then we induce an elongation onto the resistor, then which gives us a change in the resistance based on the strain. And in this case, these are commonly used in pressure sensors. So when a pressure difference between the top, you see with P, and underneath the diaphragm, when you have a finite change of pressure between the top and the bottom, this diaphragm will deflect, and then these sensors, the resistance, which you're monitoring in real time with a microprocessor that's connected directly on the same silicon chip, will give you a function of how much this diaphragm is displacing. However, it's a function of pressure. So these are already commercialized in almost every new automobile. There are several of these types of very, very small pressure sensors that are very, very sensitive because of this high gauge factor of silicon. Now, the optical displacement sensors. The most common is a laser interferometer, okay? And as the name suggests, interferometer deals with a sensor that uses interference of two beams to calculate displacement. Okay, so this is a diagram of a typical interferometer, laser-based interferometer for displacement sensing. And essentially the moving entity is on the right. It's this mirror, so you have this movable reflecting cube that's going to be attached to whatever entity is moving. So this one is moving right and left a certain distance. The system consists of a laser that generates two laser beams that are separated by a certain frequency. The laser beam is split into two pieces. We have a reference beam, F1 and F2, and the detector A. The measurement beam then continues onto the right, and it also is split between a fixed reflecting cube and the movable reflecting cube. So now you see that F1 and F2, one of these beams is going to go to the same exact setup, except one of these, if you get a displacement, is going to be moving. Okay, so F1 goes to the fixed reflecting cube, F2 goes to the movable reflecting cube. They come back and are joined again, both joined again at detector B. Okay. And this gives a more thorough description of how this system works in steps 1 through 6. But essentially what's happening is that this arrangement allows you to collect the measurement beam F2 that travels a different path between point 4 and point 6 because that cube is moving, than the fixed reflecting cube laser beam path, which is F1. So detector B will be able to detect how much the moving reflector cube has moved by processing the interference patterns that are created when F1 and F2, after moving through the reflector cubes and are joined at detector B, are joined together and analyzing the interference pattern. These are very, very sensitive sensors. Typically, you can move with accuracies that are well, less than a nanometer type of accuracy you can detect with these types of sensors, depending on how well you design all of the components. And because this is optical, the optical quality of the polarizing beam splitters and the reflecting cube also determines how much displacement changes you can resolve when you pull in both signals to detector B. Now these types of sensors are quite ubiquitous. They're used in many, many different types of microscopes. This is an example of an optical interferometer that's integrated directly with a microscope objective. And this is based on a Michelson interferometer microscope objective. So this big interferometer then is condensed down into a microscope objective. And if you're not familiar with a microscope objective, it has dimensions of a few centimeters. And when the light comes in to the microscope objective, then we also have a beam splitter, and the beam goes in one direction to a reference mirror, and it also goes into the direction it goes to the sample. As the distance between the splitter and the sample changes due to changes in your sample, both of these beams then are collected back into the microscope objective and then into the CCD camera, where an interference pattern is made. Very sensitive measurements can be made with this. So it's about collecting and analyzing interference patterns of two beams. One beam is a reference that has a fixed path length. The other beam has traveled a longer distance. When these are joined back together, you get constructive and destructive interference. Constructive interference, you get a bright band. Destructive, they cancel out, you get a dark band. And by counting these sequence of bands, you can tell how much displacement is represented by the difference in the path length. This is an explanation of that. You can read over this, so make sure that you understand the path length concept. Very simple, but it's, as I just. This is an example of an instrument that we have in the Nano Lab. It's located on the right. Not the exact system, but it does the same basic operation. Not the same manufacturer. So you can see that the sample is located on the bottom. In this case, we have a Moreau interferometer, which essentially does this same type of operation where you have a reference beam. You also have a measurement beam. The measurement beam travels a longer or shorter distance. You bring the reference and the measurement beam back together. In the lower left hand is an example of an interference where we have dark and bright fringes. So the dark fringes we get destructive interference, the bright fringes we get constructive interference. When we count these bright and dark bands, they represent distance. And with this type of instrument, then Z height differences of on the order of, let's say, an angstrom or so can be resolved in the Z direction. Lateral direction, this is limited by the diffraction resolution of light. But in the Z direction, using the interferometer, you can resolve on the order of an angstrom displacements. Or in this case, it would be a sample that has topography, because the beam will reflect off of the surface and therefore travels a different distance. Now, a very, very important concept is the optical bridge. This uses a photosensitive detector. A 4-quadrant is quite popular. It's used in every atomic force microscope and many other types of instruments and sensors. In part C, this is what 4 quadrants look like in the sensor. And essentially the photosensitive detector will, when photons are incident on one of those quadrants, you generate electron hole pairs, which is measured in the form of a current with the amplifiers. As a beam, typically a small beam, is moving, then the amount of intensity that you get between the 4 quadrants is going to change. So you use this bridge configuration between PSD 1, 2, 3, and 4. And depending on not only the XY displacement, but there can be other movements as well, then your XY output of the amplifiers are going to change. So this is really, this optical bridge is very, very similar to these classical Wheatstone bridges that we've been working with in the homework. Very powerful and used quite regularly throughout industry, particularly for atomic force microscopy. In this course, in previous years, you would have done a practicum session with atomic force microscopy, but due to technical difficulties, we were not able to include it this year. Now, photosensitive detectors, these PSDs, can also be used for triangulation. And I won't talk about this because this is a homework problem, and it's explained really well in the textbook. So see page 284 of the textbook when you're doing your homework problem. We can also do coded optical encoders, where typically we have these patterns that are located on a disk, and we have a rotating wheel with a light source, and then detectors that are located under this rotating wheel. These disks are put in the center of this, in this rotating disk, and you can generate any type of code. This is an example of binary code, gray code. And these typically are used to encode the movement of shafts and rods, and it can be done extremely sensitively. Okay, now we move on to measuring velocity. Now, the translational velocity cannot be measured directly, but we can estimate it indirectly. Okay, we can use differentiation of displacement measurements, so we know that the velocity is essentially dx dt, where x is our displacement. We can integrate the output from an accelerometer, so it measures acceleration, and we know that acceleration is equal to dv dt, so we can integrate that. And we could do conversion to a rotational velocity as well. So instead of having meters per second, we would have radians per second, and then we can convert it just by doing the 2 pi operation. Okay, so acceleration. The accelerometer is the only device that directly measures acceleration. This is an example of a single degree of freedom accelerometer. It consists of a mass, this is sometimes called a proof mass, a spring, and a damper. Okay, and we saw the transfer function for this system already in the first lecture. And most importantly to this system, you can see that the spring and the damper are connected to this frame on the outside. So it's the frame that's going to be connected to the entity that experiences an acceleration or a deceleration. When this frame, this boxed region, changes, typically this mass is already vibrating. And the vibration then is going to be a function of the mass, the damping, and the spring. When an acceleration happens, then it's going to change that resonant frequency of the vibration of this mass, spring, damper system. And then the Laplace transform of this block diagram is shown on the bottom. And you can see that in the right-hand side we have this mass and how the different forces on the mass due to the spring constant and a movement, a displacement in x, and then our damping coefficient, which is b, and the velocity, so b, v. And then the Laplace transform of this system then is ms squared xs bs xs plus k xs equals minus m. A of s is the Laplace transform of the acceleration. So the input to the system is going to be this acceleration. The output is x. Okay. Now you can see the importance of being able to derive transfer functions from these types of operations and being able to analyze those, because all of the systems, if we want to analyze their behavior and optimize their behavior, we have to be able to make a transfer function for the system and analyze this using either Laplace transform or Fourier transforms. Typically we use, for this type of system, we use a Laplace transform, and then we can take this back into the time domain by doing an inverse Laplace transform. So accelerometer sensors, primarily what I just said on the previous slide. Now, the sensor elements, the spring, mass, and the damper are connected to this housing, okay? And the ultimate goal with an accelerometer is that you're going to detect this mass displacement with respect to the accelerometer housing. So when this thing gets an acceleration or a deceleration, that's going to be acting on the body. And then the body acts on the mass through the damper and the spring, and then that mass is going to change based on how it behaves, how that system has been designed, the K, the M, and the B. Okay, so there are many different types of sensors that we can design for different applications. So in a vibration measurement, where this proof mass is vibrating, okay, and it would be a driven vibration, and we can think of this as a linear harmonic motion, and we can express this as x equal to x sub 0 sine omega t. Now, x is the displacement from an equilibrium position at any general point in time. Okay, typically we take averages for these types of things. So you've got, in a vibration measurement, you've got this mass and it's vibrating with some fundamental frequency, and it's connected to the housing. So with respect to the housing, now when the housing gets an acceleration because it's connected to a larger system, that acceleration then is going to be coupled from the housing to the mass through the spring and the damper. Okay, remember that. Then the velocity we can calculate, the acceleration we can calculate, and also peak acceleration we can calculate. Now in a vibration measurement, the vibration intensity can be measured in terms of displacement, velocity, and acceleration. Now acceleration, quite importantly, is clearly the best parameter to measure at high frequencies. And then for low frequencies, then low frequency displacements are the best way to measure. One type of sensor is called a quartz crystal microbalance. Now this is based on our piezoelectric crystal we spent time with calculating in a two-port model example. The application of a mechanical strain to the material. In this case, this is called an AT cut quartz crystal. Okay. And when you have no potential applied to this system, okay, then then you don't change the crystal at all, and you don't get this generation of charge at the plates of the electrodes, as we said before. Now, if you apply a potential to this system, the vibrational mode will be this thickness shear mode. So instead of having a, let's say, a Z type of deflection like we would have a jump rope or a rope, in this case, the displacements are going to be in the XY direction, the shear mode, the shear deformation mode. So the crystal planes in the X direction are moving back and forth with the frequency of the applied voltage. This is an example of what an AT cut quartz crystal looks like. These are something that are ubiquitous. They've been used for many, many years. They're also used, they have been used for timing circuits in electronics for many, many years. High performance electronics, these quartz crystals keep timing, and they're very, very, very precise. Now, in a quartz crystal microbalance sensor, we apply a sine wave to the crystal faces, and this causes this shear mode oscillation in the crystal. And essentially, you generate a resonant frequency, okay, F0, that can be represented as a square root of the shear modulus ratio and the density of the quartz crystal divided by 2 times the thickness of the quartz. And this can be modeled quite precisely by this simple equation. And this is an example on the lower left is the resonant frequency type of characteristic. The Q can be extremely high, the quality factor, and the quality factor is essentially estimated as the center frequency of the vibration amplitude, which is shown on the left, is the solid line, divided by the width at half the maximum amplitude. And then the circuit model, typically for a resonator, we have an RLC circuit, and then we have some parasitic capacitance in the system. And there will also be some parasitic resistance as well. But this Butterworth-Van Dyke equivalent model works quite well for these quartz crystal microbalances. So you can buy commercial instruments that allow us to measure many, many different properties on the top electrode of this system. You can read a little bit about how this works in this slide if you're interested. We won't have anything on the exam about quartz crystal microbalances, but this gives you a little introduction to these types of sensors, which are used in industry quite often. Okay, so let's talk a little bit about rotational motion measurements, rotational displacement, velocity, and acceleration. Now, for rotational displacement measurements, we can use circular or helical potentiometers. So these are very similar to the linear potentiometers, but the coils are wrapped in coils or in helical configurations to be able to detect these radial motions. We can use a rotational differential transformer, coated disc shaft encoders, and gyroscopes. An example of a circular helical potentiometer. I don't think much explanation is required here. The rotational differential transformer, you can see that the core now, instead of moving, which is this little block located between, which is rotating in this angle indicated by the arrows, and this core material, which looks like a little shoe on the end of this rod, is rotating, and it's going to change as it's rotating the coupling between the primary coil on the left and the secondary coils on the right. So this is very similar to our linear displacement detection, except now that this core is rotating in a circle. And you can imagine that you can make much more sophisticated types of arrangements where we have the secondary coils that are actually forming a circular pattern, and you can make these much more sensitive. But for the concepts, you can see that we can do rotational differential transformers as well. And then coated disc shaft encoders, we can also do the same types of operations that you saw earlier in the lecture. Now gyroscopes. Gyroscopes are an important area for measuring rotations, type of sensor, especially for miniature gyroscopes now. With these miniature silicon-based sensors, gyroscopes have become extremely sensitive and very precise to rotations. Now, gyroscopes measure both absolute angular displacement and absolute angular velocity. They consist of a motor-driven wheel whose angular momentum is such that the axis of rotation tends to remain fixed, thus acting at a particular reference point. Now, so basically you have something that's spinning, that's fixed, and then we have a frame, and the frame is attached to the body whose motion is to be measured. So think of a bicycle wheel. Now, if you spin the bicycle wheel and you put the two nuts that usually clamp to the fork in your bicycle, and you put those into your hands and you spin the wheel, try to rotate your hands in a circular pattern, and the wheel will respond with a force. Okay, this is this Coriolis force that's acting upon your hands due to this rotating wheel. Okay, this is the same concept. The frame is attached to this spinning disc, and as that moves, the disc is going to exert a particular force that can be measured with a particular sensor. Okay, so the gyro frame is attached to the body whose motion is to be measured. The output is measured in terms of the angle between the frame and the axis spinning wheel. So when you have a spinning wheel and you have some motion, then depending on the speed of the wheel, then the displacement that we get in this system is going to depend on how that force from the wheel acts upon the frame due to the motion. The free gyro and the rate integrating gyro measure angular displacement, and a vibrating gyro measures angular velocity. So we can also have things that are vibrating, okay? And these are for your own information. I will not include gyroscopes on a homework or an exam, but they're quite an important component or sensor that you may actually come across in your professional careers if you're working as an electrical engineer. Free rotor gyroscope, you can see the rotor in the center and the spin axis of the rotor. Okay. Now, the key to this, again, is the frame. And the frame in this case would have been your body, your arms attached to the lug nuts of the spinning bicycle wheel. Okay. And the output axis then, due to the torque that's applied on the input axis, is going to be a function of the frequency and this rotation, and this is called precession. And this is probably not making any sense to you, but you have to read and it'll take some time for you to understand that we have a couple of things going on. We have this rotating disc in the center that's connected to a body. This body then has some torque that's applied to it through the input axis. And due to the spinning disc, the disc is going to generate a torque opposite to the applied torque through the frame that can be measured. This is called the precession, and the output axis is located on the right-hand side, and the torque that it generates is due to the inertia of the system, the spinning disk frequency, and then this omega, which is the angle. Now, from Newton's law of motion for rotation, the time rate of change of angular momentum about any given axis is equal to the applied torque about the given axis. Okay. Now, we also have vibrating gyroscopes, and these are quite important for miniature sensors. And the upper diagram shows that when you have this sensor, which is a resonating ring, let's say, and this ring is basically resonating in plane. So you can see in diagram C on the right-hand side, this plate is going to be flat, but it's vibrating in the lateral direction, so you can't see. So it's moving in the lateral direction, it's vibrating. Now, when we get this Coriolis acceleration, so basically we've got this vibrating disc in this frame, and then the frame is rotated, then the acceleration is going to cause changes in the vibration mode of this disc, and that's represented in diagram D, E, and F. These vibration modes are going to change as different Coriolis acceleration due to velocity and angular movement And we can detect those different vibration modes electronically. So then we can map those different vibration modes due to the motion of the frame that changes the vibration frequency as this angular momentum is applied to the frame. Okay. And then this is another vibrating gyroscope, and it operates in the same basic way, except this time the vibratory axis, this thing is vibrating theta. We have electrodes. Gimbal structure is actually the frame structure, and then in this case the input axis is an inertia or an angular rate. If you're interested, you can read a little more about this. Now we have optical gyroscopes, Sagnac effect, and essentially this is just based on an optical path, let's say in an optical ring. This could be an optical waveguide structure. And we have two laser light beams that propagate in opposite directions in the ring. And the ring has an index of refraction in a particular radius. One beam goes in a clockwise direction and the other in a counterclockwise. It turns out that for certain angular rotations, you can measure the time it takes this laser beam to traverse in a particular direction, the difference in the length that it travels based on the angular rotation of this ring. And that's given in this equation on the left-hand side, this delta L. So the distance that the laser beams travel can be altered by putting this into an angular momentum. These can be very, very sensitive, and they can be made very, very small. The problem with this is typically generating a good quality laser beam into the optical path. This is called a ring laser gyroscopes, where you have a He or helium neon gas mixture inside the core of these tubes. These are called laser gain tubes. And then we have a two anode cathode laser beam generation. And then we have these mirrors. And essentially the same type of situation will happen. This gyroscope is going to be moving, and then you essentially are going to be measuring the displacement of the opposite going, the frequency of these opposite going laser beams, and depending on the rotation, then you can measure the angular speed based on the two differing laser beams inside these laser gain tubes. Same concepts. Okay, that concludes the translational motion description, and we'll go on now to the second half of the lecture, mass, force, and torque measurements. And essentially these are things, the instruments that I'll talk about today, mass, force, and torque, are much older concepts. So a lot of the instrumentation that we have today, maybe you've seen in the laboratory before. For measuring mass, I'll talk a little bit about something called a load cell. For measuring force, I'll talk again about the accelerometer and a vibrating wire sensor for measuring force, which will be also a homework problem. And then measurement of applied torques by rotating bodies. So again, the quantities in units of distance, force, motion, and torque. So mass describes the quantity of matter that a body contains, and the most common way to measure mass is using a load cell of some sort. Most load cells today are electronic, though some of the older pneumatic or hydraulic types also exist for usually things that are extremely large. But electronics, as in many fields, has dominated in the load cell industry. In an electronic load cell, the gravitational force in the body being measured is applied to an elastic element. Could be a strain sensor, this type of thing. And then its response to the mass is then measured. And then, of course, then we have to calibrate. We always have to calibrate these types of sensors. We don't make absolute measurements. We make reference measurements from a calibration. So typically when we have a load cell, we have a set of weights of a certain kilogram range, and then we do a calibration curve for this sensor over the kilogram range or the mass range, the weight range that we're going to be measuring. So these are different types of elastic elements that can be used in a load cell. So these load cells come in both compression and tension form. So compression is something that's being pushed together, and tension is being something that's kind of pulled apart. In these compression type, the mass is put on a platform, for example, that's showed on the bottom. In a tension type, something is, let's say you have a scale that you hang from the ceiling, and you pull, the weight is going to pull this sensor and apply tension to it. So typically we can use a displacement transducer to measure these deflections of the elastic elements. So strain gauge, for example, we can use force transducers based on LVDTs. We can use a piezoelectric displacement sensor, things that we've already seen. Now we can start building these components up into real systems that are used in industry. An example of a pneumatic is on the left, which is air, right? And one that's based on hydraulic, which is a fluid. And basically, what happens in the pneumatic is you have an air supply. You're going to fill this little cavity. When you put a force onto the bottom of this thing, you're going to change the pressure by deflecting the displacement. You're going to be deflecting this membrane down, and the volume is going to be changing. It's going to be decreasing, so then your pressure is going to increase. And making a calibration curve, then you can get an estimation of how much force due to a mass has been applied. Same basic concept for hydraulic, except now a sealed system, a fluid, and essentially when you decrease the volume in the cavity, then your pressure is going to increase. Now for force measurements, the piezoelectric transducer can be used. This is quite common. And also we can use the mass M that we saw earlier of the accelerometer. Okay. So piezoelectric force sensors are quite important. Now, as we know now from all of our lectures, when the crystal is compressed, a charge is generated on the plates, right? We have electrodes. And then this charge that is generated on the plates then results in an output voltage. Now, as we know that when we apply charges to those plates, it's going to leak away eventually through our measurement circuit. Because of this characteristic, piezoelectric transducers are not typically suitable for measuring static or slowly varying displacements, because you will lose your charge that you generate, because it will just leak through your readout electronics. It'll find a path for all the charge to leak out. This is an example of some piezoelectric force sensors. This is a crystal plate on the upper left-hand corner. We have an AT cut plate in part A, a readout, and then a packaged. So piezoelectric force sensors have been around for many, many years, and they're quite common. You can buy these commercially. And their characteristics are very well known. So you can read a little bit more about this in the book. Now, accelerometers, as we've been talking about throughout the course, really. Now, acceleration is a dynamic characteristic of an object because according to Newton's second law, it essentially requires the application of a force. F is equal to ma. In effect, the position, velocity, and acceleration are all related, right, through time derivatives. However, in a noisy environment, taking derivatives may result in extremely high errors. Taking a derivative when you don't have something that's smoothly varying can lead to huge errors. Therefore, velocity and acceleration are not taken from these displacement sensors, because then we would have to take direct derivatives. Rather, we measure these by special vibration sensors, as the accelerometer, as we've seen so many cases. So you've seen this, you've seen the block diagram with the dynamic system containing the spring, mass, and damper, and then connected to the body. Now, if we go in now a little bit deeper, we take our Laplace transformation of the differential equation representing the system response to an acceleration a sub s. Then we can basically derive the transfer function of the system g of s, which is equal to output over the input, right? In this case, the output is x of s. The input is the acceleration. And so how we design our transfer function system will dictate how the output will respond based on the input, a sub s. So this g sub s is equal to negative 1 over s squared plus 2 eta omega naught s plus omega naught square. Now, we know that omega naught squared is related to the resonant frequency of this, the fundamental resonant frequency of the system. And then we also have this damping term as well. So these are our tweaking parameters that we use to adjust the response of the system due to a particular acceleration. So then our fundamental frequency, and then we can see this term that we have for the damping term is related to this b over the mass. Okay, and then we can take an inverse Laplace transform, and we get our output signal x of t, input inverse Laplace transform of g of s times a of s, and then we can see that in the time domain, this simply has the integration of the transfer function minus t minus tau acceleration with our integrating factor tau. Okay? Then we can have two solutions, one for the underdamped case and one for the overdamped case. Now, depending on how you want your sensor to respond. Then we started adjusting the resonant frequency, the fundamental resonant frequency, and also the damping term. So in the accelerometer characteristics, a correctly designed accelerometer should have one clearly defined resonant frequency, f sub n. And in the area of frequency where we want to do our measurement, we typically want a flat band between lower than our resonant frequency. And you can see it in the lower diagram on the right. So remember when we did our second order transfer function characteristics, we saw this general response, second order system, that was dependent on the damping and the resonant frequency. And the resonant frequency came from K and M. The damping came from B and M. Okay, within this flat region, as the vibrating frequency changes, the output of the sensor will correctly reflect the change without multiplying the signal by any variations in the frequency characteristic. So what that means is the transfer function of your system should not affect the output frequency change when the vibration is changed due to a change in acceleration to the frame. If you're doing your detection to the right of the fundamental frequency, you can see that it's going to be, the output is going to be greatly affected just by the transfer function of the system, and that's not what you want. So you don't want your transfer function of your system to change over frequency range that you want to detect. So this is really, think of this as the pass band of the mechanical transfer function for the frequency range that we want to detect, and it's typically below this resonant frequency f sub n. So we're going to now look at some different types of accelerometers: capacitive, piezoresistive, piezoelectric, and thermal. A capacitive accelerometer, it basically has a base cap and a mass, and mass is the part that's going to be vibrating, for example. These thinned areas in the mass actually act as mechanical springs. Okay, when the mass moves towards the upper plate and away from the base, the spacing changes. So now we see we have this capacitive type of sensor where we have a differential capacitance that we're going to be reading out. So the circuit that we've used in the homework, now we can actually use this to read out the capacitive accelerometer. And essentially, as we've seen before, the capacitive accelerometer, we have two capacitors, these two differential capacitors. One is from the base, one is from the cap. And you can see that we have now a transistor network on the input and then also in the feedback loop. Okay. Now, this is a switch capacitor implementation of a capacitive accelerometer, and these pass transistors in the feedback loop, the resistance of the pass region is controlled by voltages phi 2, 3, and phi 3 hat. And you can have a very precise implementation, very small, using switch capacitive circuits, CMOS technology, to control the feedback loop in this system. And then, of course, we have a conventional capacitor. And then we also have the same type of control network at the input of our system. So then we get a similar type of relationship with the output with respect to the change of the capacitances. And from the homework, you know that this CMC minus CMB is also a function of the displacements of the plates. So you will expect, I think you should expect um, more of this type of analysis of these differential capacitive sensors where we have to derive an output based on a change in capacitance. Okay, and the last example is a vibrating wire, and this is a homework, and essentially what we have is we have a permanent magnet, okay, and then we have a wire, okay. The resonant frequency of the wire depends on, so it's kept oscillating, essentially. It has an applied force to it, so it actually has a tension being applied through force F. And the resonant frequency you can see in the square root is has an effect on the resonant frequency. So the more torque that you apply to the system, then your resonant frequency will decrease. And essentially, so you have this wire that's kept vibrating, okay, and then you use the magnets for some reason. So it's for your readout or it's for some other reason. So I want you to think about, you know, inductance and how the wire will affect the inductance and how this thing would be read out. And this will be on your homework problem. And of course, like usual, like always, if you have more questions, I will give you hints, but you have to send me an email. But take some time to try to figure out how this thing is working. So you have a wire that's oscillating between a core air area between a north and a south pole of a permanent magnet. So we need to be able to read this thing out. How are we going to do that? So that's the end of lecture 8. Thank you.